Welcome to this coding session. In this video, we'll be diving into LeetCode problem number 100, titled Same Tree. This problem challenges us to determine if two binary trees are structurally identical and have the same node values. It's a common and essential question that helps in mastering tree traversal techniques. Let's get started. The problem asks us to compare the roots of two binary trees, denoted as P and Q, and determine if the two trees are the same. For two trees to be considered the same, they must meet two criteria. They must be structurally identical, meaning their shapes match exactly, and the values of all corresponding nodes in the trees must also be the same. The function we need to write should take the roots of these two trees as input and return a Boolean value, true if the trees are the same and false otherwise. For the input, we have two parameters, P, which represents the root of the first tree, and Q, which represents the root of the second tree. The output is a Boolean value that directly answers whether the two trees are the same or not. Let's first look at an example where the two trees are the same. Here, tree P and tree Q both have the same structure and the same values at every corresponding node. The root node has a value of 1, and it has two children. The left child has a value of 2, and the right child has a value of 3. Since both the structure and the values of the nodes match perfectly between the two trees, the function would return true as the output. Now, consider a case where the two trees are not the same. In this example, tree P has a root node with a value of 1, a left child with a value of 2, and a right child that is null. Tree Q, on the other hand, also has a root node with a value of 1, but the left child is null, and the right child has a value of 2. Even though the root values match, the overall structure of the trees is different. Because of this mismatch in structure, the function would return false as the output. In another example, tree P consists of a single node with a value of 1, while tree Q is completely empty, represented by null. Since tree P has one node and tree Q has none, they do not meet the criteria of being structurally identical, and the function would return false. This demonstrates that if one tree is empty and the other is not, the two trees are not considered the same. To summarize, there are a few important constraints and edge cases to consider. The number of nodes in both trees will range between 0 and 100, and the value of each node will be an integer between -10,000 and 10,000. For edge cases, if both trees are empty, the function should return true. If one tree is empty and the other is not, it should return false. If the trees have the same structure but differing node values, the result is false. Finally, for trees with only one node each, the function should return true if the node values are the same and false otherwise. To determine if two binary trees are the same, we need to verify that they are structurally identical and that their corresponding nodes have the same values. One natural approach to solving this problem is through recursive tree traversal. Since binary trees themselves are recursive in nature, this method aligns well with their structure. The idea is to perform a pre-order traversal, visiting the current node, then the left subtree, and finally the right subtree, while comparing nodes from both trees at each step. If both nodes are null, it means the trees end at the same point, so we return true. However, if one node is null and the other is not, the trees differ structurally, and we return false. Similarly, if both nodes exist but their values differ, the trees are not the same, and we return false. Otherwise, we recursively compare the left and right subtrees and combine the results to determine if the trees are identical overall. The recursive approach has a time complexity of O(n), where n is the total number of nodes in the smaller tree, as we need to visit each node exactly once. The space complexity is O(h), where h is the height of the tree, because the recursion stack grows proportionally to the depth of the tree. Another way to solve this problem is through an iterative approach using breadth-first search, or BFS. Instead of recursion, we use a queue to traverse both trees level by level. At each step, we compare nodes from both trees. If one node is null while the other is not, or if their values differ, we immediately return false. Otherwise, we enqueue their left and right children for further comparison. This continues until the queue is empty, and if no mismatches are found, we conclude that the trees are the same. This method avoids recursion but requires managing the queue to track nodes at each level. For the iterative BFS approach, the time complexity remains O(n), as we still need to traverse all nodes in both trees. The space complexity, however, is O(W), where W is the maximum width of the tree. This width corresponds to the maximum number of nodes present at any level, which determines the size of the queue. After considering both approaches, the recursive strategy stands out as the most natural and intuitive solution. Binary trees are inherently recursive structures, and a depth-first traversal, such as pre-order traversal, aligns perfectly with the problem requirements. Additionally, this approach is simpler to implement and leads to clean, efficient code. The recursive method ensures that both trees are structurally identical by comparing the left and right subtrees recursively at every level, and the values of the corresponding nodes are checked along the way. While both the recursive and iterative approaches have the same time complexity of O(n), the recursive solution is often preferred due to its simplicity and elegance. It avoids the added complexity of managing a queue, which is required in the iterative BFS approach. From a space perspective, the recursive approach uses space proportional to the height of the tree, O(h), while the iterative method depends on the tree's maximum width, O(W). In balanced trees, where the height is O log n and the width is O(n), recursion is generally more space efficient. However, in skewed trees, both approaches can use up to O(n) space. One trade-off to consider is that the recursive solution may lead to stack overflow for extremely deep trees if the recursion depth exceeds the system's limit. In such cases, the iterative BFS approach becomes a practical alternative. Ultimately, we choose the recursive method for its simplicity and alignment with tree traversal, while keeping the iterative solution in mind for environments with strict recursion limits. To solve the problem of determining if two binary trees are the same, we first need to understand the criteria that define sameness. Two binary trees are considered structurally identical if both trees have the exact same structure, meaning nodes appear at the same positions in both trees, and the values at corresponding nodes are equal. To approach this problem, we can use a recursive tree traversal method. Recursion is particularly effective here because it allows us to simultaneously explore the structure and values of both trees layer by layer. The first step is the base case. If both trees are empty, meaning their roots are none, they are inherently identical, so we return true. However, if one tree is empty while the other is not, then they can't be identical, and we return false. Next, we check the current node values. If both nodes exist, we compare their values. If the values don't match, we can conclude the trees are not the same and return false immediately. After verifying the current node values, the next step is to recursively check the subtrees. First, we focus on the left subtrees. We compare the left child of the root node in the first tree with the left child of the root node in the second tree by making a recursive call to our function with these left subtrees as input. Once the left subtrees are processed, we do the same for the right subtrees, comparing the right child of the first tree's root with the right child of the second tree's root, again using recursion. The results of these recursive calls are combined to determine the overall result. Specifically, the trees are structurally identical if and only if the current node values are equal, the left subtrees are structurally identical, and the right subtrees are structurally identical. If all these conditions are satisfied, we return true. Otherwise, we return false. The pseudocode provided here outlines these steps. First, check for base cases, then verify the current node values, and finally recurse on the left and right subtrees. This final return statement in the pseudocode combines all the conditions we discussed. It checks that the current node values are equal and that both the left and right subtrees are identical by making recursive calls. This highlights the recursive nature of binary trees. They are naturally suited to recursive algorithms because each subtree is itself a binary tree, allowing us to solve the problem in smaller chunks. This approach follows the divide and conquer principle. We divide the problem into smaller subproblems, comparing the left and right subtrees, and solve each one recursively. Handling the base cases, such as when one or both trees are empty, is critical to avoid unnecessary computations and to ensure correctness. Another key insight is that recursion allows for short-circuiting. The algorithm terminates as soon as it finds a mismatch in either node values or structure, making it efficient. Finally, understanding the underlying data structure is important. Each binary tree node contains a value and pointers to its left and right children, which form the building blocks for this recursive approach. Recursion, while powerful, relies on the call stack to manage its progress. Each recursive call adds to the stack, and the maximum depth of the stack corresponds to the height of the tree. In a balanced tree, this depth is proportional to O log n, but in the worst case of a skewed tree, it can grow to O n, where n is the number of nodes. This space complexity is a direct result of the recursion. For the time complexity, the algorithm visits each node exactly once and performs constant time operations for each node, leading to an overall time complexity of O n. Additionally, this algorithm handles various edge cases effectively. For example, it correctly identifies that two empty trees are identical, while one empty and one non-empty tree are not. It also catches mismatched structures, such as when one tree has a child node while the other does not, and ensures that trees with the same structure but different node values return false. Even simple cases like comparing single-node trees are covered, demonstrating the algorithm's robustness and versatility. Let's walk through an example to see the algorithm in action. Consider two binary trees. The first tree has root node 1 with left child 2 and right child 3. The second tree has the same structure and values. We start by comparing the root nodes. Both have the value 1, so we proceed to compare their left and right subtrees. For the left subtree, we compare the nodes with value 2. Both nodes match, and since their children are none, we return true for the left subtree comparison. Next, we move to the right subtree and compare the nodes with value 3. Again, both nodes match, and their children are none, so the right subtree comparison also returns true. Since the root node values match and both the left and right subtree comparisons return true, we conclude that the two trees are structurally identical. The final output is true. This Python implementation solves LeetCode problem number 100, same tree, which determines if two binary trees are structurally identical and their corresponding nodes contain the same values. The treeNode class is used to define the structure of a binary tree node. It has three attributes, val for the node's value, and left and right pointers for the left and right child nodes, respectively. This is the standard representation for binary trees in LeetCode. The isSameTree method of the solution class performs the comparison. It takes two input parameters, p and q, representing the root nodes of the two binary trees to compare. The function uses recursion to traverse both trees simultaneously and compare their structures and values. The base case checks if both p and q are none. If both are none, it means we've reached the end of a branch in both trees, and they are identical at this point, so the function returns true. If one of the nodes is none while the other is not, it means the trees differ in structure at this point, so the function returns false. Next, the function compares the values of the current nodes, p.val and q.val. If the values are different, the trees are not identical, and the function returns false. Finally, the function makes recursive calls to isSameTree for the left children, p.left and q.left, and the right children, p.right and q.right. The results of these recursive calls are combined using a logical AND operator. This ensures that both the left and right subtrees must be identical for the entire trees to be considered identical. This algorithm ensures that every node in both trees is visited exactly once, resulting in a time complexity of O n, where n is the total number of nodes in the larger tree. The space complexity is O h, where h is the height of the tree, due to the recursive call stack. Here, we start with the Java implementation for the problem. First, we define a nested static class called treeNode, which represents the structure of a binary tree node. It contains three fields, an integer val to store the value of the node, and two references, left and right, pointing to the left and right child nodes, respectively. The treeNode class has two constructors, one that initializes the node with just a value and another that initializes it with a value as well as left and right child nodes. Next, we move to the method isSameTree, which determines if two binary trees, represented by their root nodes p and q, are identical. The first check in this method looks at whether both nodes are null. If they are, it means we've reached the end of a branch in both trees simultaneously, which indicates that this part of the trees is identical, so we return true. The next check handles the case where one node is null but the other isn't. This would mean the trees have a structural mismatch at this point, so we return false. Now, we handle the case where both nodes are non-null. If the values stored in the nodes, p.val and q.val, are different, it means the trees differ at this point, so we return false. If the values are the same, we need to verify that the subtrees are also identical. To do this, we recursively call the isSameTree method for the left subtrees of P and Q, as well as for their right subtrees. The final return statement uses a logical and to combine these recursive calls, ensuring that both the left and right subtrees must be identical for the current nodes to be considered part of the same tree. This completes our implementation, which efficiently checks for tree equality using recursion. Here, we have two trees, P and Q, both represented as 1, 2, 3. Visually, they look identical, with the root node having a value of 1, and two child nodes with values 2 and 3. To determine if these trees are the same, we start by comparing the root nodes. Both have the value 1, so we proceed to check their left and right subtrees. For the left subtree, both nodes have the value 2, and since neither has any children, we return true for this subtree. Similarly, in the right subtree, both nodes have the value 3 and no children, so we return true for this subtree as well. Since both the left and right subtrees return true, the entire trees are identical, and the final output is true. In this example, the trees P and Q differ structurally. Tree P has a left child with the value 2, while tree Q has a right child with the same value. Both trees have the root node 1, so we begin by checking their left and right subtrees. For the left subtree, tree P has a node with the value 2, but tree Q has no corresponding node, represented as none. This mismatch immediately tells us the left subtrees are not the same, so we return false for the left subtree. Because the left subtree returned false, we don't need to check the right subtree further. The trees are not identical, and the output is false. Now we have two completely different trees. Tree P has the structure 1, 2, 1, while tree Q is structured as 1, 1, 2. Both trees start with a root node of 1, so we continue by comparing their left and right subtrees. In the left subtree, tree P has a node with the value 2, while tree Q has a node with the value 1. Since these values are not equal, we return false for the left subtree. With the left subtree already determined as not identical, there's no need to evaluate the right subtree further. The final result is that the trees are not identical, and the output is false. The solution fundamentally relies on recursion to compare the nodes of both trees at the same time. If both nodes being compared are none, this indicates that the trees are identical at that specific point. However, if one node is none while the other is not, or if the values of the nodes differ, the trees are immediately determined to be different. The algorithm then recursively checks both the left and right subtrees. For the entire trees to be considered identical, both of these recursive checks must return true, ensuring that every corresponding node in both trees meets the criteria for equality. The time complexity of the isSameTree function is determined by how it traverses the two trees, P and Q. Since the function uses depth-first traversal, it explores every node in both trees. Let's define n as the total number of nodes in tree P and m as the total number of nodes in tree Q. In the worst-case scenario, when both trees are fully traversed, the function visits each node once. At each recursive call, a single node from both trees is processed. This includes checking if the nodes are null, comparing their values, and making recursive calls for the left and right children. Each of these operations takes constant time, or O1, per node. Therefore, the total time complexity depends on the number of recursive calls, which is proportional to the smaller tree size. If one tree is smaller, the traversal stops early when that tree is fully processed. As a result, the time complexity is O, min, n, m, where the function performs fewer operations if one tree is smaller than the other. Now, let's analyze the space complexity, which is primarily influenced by the recursion. Each recursive call adds a frame to the call stack, and the maximum number of frames corresponds to the depth of the recursion. This depth is equal to the height of the smaller tree. For a balanced binary tree with k nodes, the height is approximately log k, but for a skewed tree, which is completely unbalanced, the height could be as large as k. Therefore, the recursion depth can vary depending on the tree's structure. In general, the maximum depth is O(h), where h is the height of the smaller tree. Additionally, the function doesn't use any other data structures, so the auxiliary space is O(1). Combining these factors, the overall space complexity is O(h), where h represents the height of the smaller tree. This gives us an efficient space usage that scales with the tree's height. To better understand how the function performs under different scenarios, let's consider the best, average, and worst cases. In the best case, the trees differ immediately at the root. The function detects this in constant time, resulting in O1 time and space. For the average case, the trees are similar initially but diverge at some intermediate level. Here, the function performs recursive checks up to that level, which leads to a time and space complexity of O, min, n, and m. In the worst-case scenario, the trees are identical, requiring the function to traverse all nodes in both trees. This results in a time complexity of O, min, n, m, and a space complexity of O, h, where h is the height of the smaller tree. If we compare this solution to a naive approach that uses in-order traversal to store node values in lists, the naive method would require additional space proportional to the total number of nodes, or O, n plus m. It would also have a time complexity of O, n plus m, for traversal and comparison. Our solution avoids this extra space usage by performing comparisons during traversal, making it more efficient with O, min, n, m, time and O, h, space. Finally, let's justify these big O bounds for the algorithm. The time complexity of O, min, n, and m comes from the fact that each node is visited exactly once during the depth-first traversal. The function stops processing as soon as one of the trees is fully traversed, making the total operations proportional to the size of the smaller tree. For space complexity, the recursion contributes to the call stack, and the maximum depth of the stack corresponds to the height of the smaller tree. This gives a space complexity of O, h, where h is the height of the smaller tree. Together, these bounds demonstrate that the algorithm is optimal for recursively comparing two binary trees, as it minimizes both time and space usage while ensuring correctness. When comparing two trees, there are a few common mistakes that can lead to incorrect results. One major issue is confusing structural comparison with value comparison. It's not enough for the node values to match, the overall structure of the trees must also be identical. For instance, if tree A has a root value of 1 with a left child 2, and tree B also has a root value of 1 but the 2 is on the right instead, these trees are not the same because their structures differ. Another frequent mistake is failing to handle null nodes properly. If you don't check for null nodes explicitly, you risk runtime errors or inaccurate comparisons. Always ensure you're traversing both trees simultaneously and account for null nodes in your logic. Inefficient tree traversal is another pitfall. Some solutions traverse the same parts of the tree multiple times unnecessarily, which increases time complexity. Aim to traverse each node just once. Finally, overcomplicating the base case in a recursive solution is a common issue. The base case is simple: if both nodes are null, return true; if one node is null but the other is not, return false. Keeping this logic clear and straightforward is key to avoiding errors. Edge cases are another important consideration. For example, comparing two empty trees should return true, while comparing one empty tree to a non-empty tree should return false. Similarly, trees with only a single node need to be handled correctly. Testing these scenarios ensures your solution is robust. From an interviewer's perspective, this problem is as much about how you think as it is about the result. It's a classic example of tree traversal, so consider how you would manually compare two trees node by node. Recursive solutions are often the most natural and efficient for this type of problem. Interviewers are also looking for clean and readable code, so avoid redundant checks and aim for simplicity and clarity. Additionally, be prepared for follow-up questions that build on the core problem, such as determining if one tree is a subtree of another or comparing trees based on other attributes, like whether they are height-balanced. While recursion is a common approach, discussing iterative solutions using a stack or queue can demonstrate a deeper understanding of tree traversal techniques. This problem is closely related to other popular tree problems. For instance, the subtree of another tree problem asks whether one tree is a subtree of another, which builds directly on the concepts used in same tree. Another example is invert binary tree, which involves flipping the left and right subtrees, a simpler problem to help you practice tree manipulations. There's also symmetric tree, where you check if a tree is symmetric around its center. These problems share similar traversal techniques and can help reinforce your understanding. Now, when it comes to solving same tree, the recursive approach is the most intuitive. You compare the root nodes first, and then recursively check the left and right subtrees. This method is efficient, with a time complexity of O(n), where n is the total number of nodes, and a space complexity of O(h), where h is the tree's height due to the recursive call stack. Alternatively, you can use an iterative approach, simulating recursion with a stack or queue. While this avoids the risk of stack overflow for very deep trees, it can be slightly more complex to implement because you need to manage the traversal explicitly. Another approach worth mentioning is serialization and comparison. This involves serializing both trees into strings using a specific traversal order, such as preorder, and then comparing the serialized strings. This method can be easier to implement since you convert the entire tree structure into a single format. However, it comes with a trade-off in terms of efficiency, specifically, space usage. Storing the entire tree as a string representation requires extra memory, which could be significant for large trees. While this approach may be less efficient, it's a useful alternative to consider, especially for simpler implementations or unique constraints in certain problems. Great job! In summary, we explored a recursive approach to check if two binary trees are the same by comparing their structure and node values. This problem is a great exercise in tree traversal and recursion. Remember to practice similar problems to solidify your understanding. Thanks for joining, and don't forget to like, share, and subscribe for more content like this. That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!